Hey guys, Assalamu alaikum wa rahmatullah. Chapter 23, Gauss law, problem number 26. We have a diagram here. Figure A shows a narrow charged solid cylinder that is coaxial with a larger charged cylindrical shell. So we have a very small narrow cylinder here, solid cylinder, and then surrounded by a coaxial cylindrical shell. Okay. Both are non-conducting and thin, so both are thin and have uniform surface charge densities on their outer surfaces. Okay, so both of them are charged on their outer surfaces with some charge density, whatever that is to be found basically. Figure B gives the radial component E of the electric field versus the radial distance R from the common axes, and ES is equal to 3 into 10 to the power 3 Newton per meter. So ES is here, that is 3 into 10 to the power 3 Newton per coulomb. What is the shell's linear charge density? We have to find out linear charge density of the cylindrical shell. That means this outer one. Okay, that means this outer one. Now we have 3 divisions up to ES, 1, 2 and 3. So 3 divisions make 3 into 10 to the power 3 Newton per coulomb, which would simply mean 1 division is 1 into 10 to the power 3. So this one division is 1 into 10 to the power 3. The second division is 2 into 10 to the power 3. And similarly this one is minus 1 into 10 to the power 3. Then minus 2 into 10 to the power 3 and so on, minus 3 into 10 to the power 3. Now, you can see how field varies because of this system. Now, we must be aware, you must be aware, or you must have done it while going through this chapter. If we consider a cylinder, okay, if we consider a cylinder, a hollow cylinder, if we consider a hollow cylinder with some charge on its surface, okay, with some charge on its surface, then how does this cylinder behave if it is an infinite cylinder? How does this cylinder behave? What is the field because of this cylinder? Inside, now this is a very simple derivation from Gauss law. I'm sure you must have done that. Field inside the cylinder, inside the hollow cylinder is 0. Okay, and outside it behaves as a line charge along its axis. Okay, so it behaves like a line charge along its axis. It behaves like a line charge along its axis. That would mean field outside is same as that of a line charge. So that would be lambda divided by 2 pi epsilon 0 r. So you must, I'm sure you are aware of this. Field inside a hollow cylinder is 0 and field outside is same as that of a line charge. So cylinder behaves like a line charge along its axis. Now, if we consider this system, if I show you the cross-sectional view of this system, we have a solid cylinder here, and then this is surrounded by a cylindrical shell. Okay, this is surrounded by a cylindrical shell. The two are concentric, so let me draw it here. This is a cross-sectional view. This is charged from outside. Let's suppose positively charged. I'm not sure if it's positively charged or not. We'll come to know about that. Okay, so I'm just assuming this is positively charged, and this is having some charge, maybe positively charged also. Okay, we have to see that if it is positive or negative. Now, if I consider a point somewhere here, inside this outer cylinder, inside this, so the point can be infinitely close to the surface but on the inner side, then field due to this cylinder will be 0 and there will be field only because of this solid cylinder along its axis. So this field, and we can see there is a sharp change at a distance of 3.5 meters. Okay, why is the sharp change in this graph? Just before 3.5 field is here, 1 into 10 to the power 3, and just after 3.5 field is here, minus 2 into 10 to the power 3. So that transition is only when you are going from this point here, which is infinitely close to the surface, this point here, infinitely close to the surface but on its inner side, and then you are just outside the surface, again infinitely close to the surface but just on the outside. Okay, so field here, Due to this due to this cylindrical shell is 0, but then there will be field at this point from the outer side. So here at this point, point number 1, which is infinitely close to the surface, but on the inner side, field will be only because of this cylinder here. Then field at point number 2, which is just outside the surface of the cylindrical shell, field will be because of the both, So that's the reason the sharp change is there. So we also come to know that this distance, this radius of the outer cylinder must be 3.5 meters. Okay, this must be 3.5 meters. Okay, so we have to find out line charge density of this cylinder. Okay, we have to find out line charge density of this cylinder. Now that's what we'll do here. I'll consider a point just inside this outer cylinder. Okay, just inside this cylinder. I'll consider a point just inside the cylinder. That means at r equal to 3.5 minus meters. 3.5 minus is a little less than 3.5. Okay, a little less than, only a little, in just teeny little bit less than 3.5. Okay, if you are a little less than 3.5, that means you are on the inner side. That means field will be only because of this this charge cylinder here. And field because of the solid cylinder, we already know, I'll call this E1 is equal to lambda 1, I'll call this one having charge density lambda 1 divided by 2 pi epsilon 0 r. 2 pi epsilon 0 r. And r is 3.5. Okay. Now this thing from the graph is 1 into 10 to the power 3. 1 into 10 to the power 3. So if we are asked to find out linear charge density of the solid cylinder here, this is the equation. Just substitute, transfer this 2 pi epsilon 0 r here, we will find out lambda 1. Substitute the values, that's it. But we are not asked to find out lambda 1, we are asked to find out lambda 2, linear charge density of this outer cylinder. Okay, now let's do that. Let's consider point 2 now. Okay, let's consider point 2. Point 2 is at a distance of a little greater than 3.5 meters. Only that teeny little greater than 3.5 meters. Teeny little greater than 3.5 means you are just outside the surface. And our field will be because of this one as well as because of this one. So I'll call that E2. E2 will be now lambda 1 plus lambda 2 divided by 2 pi epsilon 0 r. Okay, 2 pi epsilon 0 r. Remember, field due to this cylinder will be lambda 1 divided by 2 pi epsilon 0 r, and since point 2 is just outside the cylinder, so this will also behave like a line charge along its axis. So along the axis we will have total line charge density as lambda 1 plus lambda 2. So lambda 1 plus lambda 2 divided by 2 pi epsilon 0 r, and this is equal to here. A little greater than 3.5 is minus 2 into 10 to the power 3. That means this charge is not positive. Okay, this charge is not positive. So minus 2 into 10 to the power plus 3, yes, plus 3. Minus 2 into 10 to the power plus 3. We had find out lambda 2. Okay, we had find out lambda 2. So we need to get rid of lambda 1. So simple, we'll solve the two equations. Call this equation 1 and this one equation 2. We'll subtract the two equations. Okay. Equation 2 minus equation 1. Lambda 1 divided by 2 pi epsilon 0 r, lambda 1 divided by 2 pi epsilon 0 r will cancel out. So we'll be left with lambda 2 divided by 2 pi epsilon 0 r. So lambda 2 divided by 2 pi epsilon 0 r is equal to this thing minus this thing. So minus 2 minus 1 is minus 3. Minus 3 into 10 to the power 3. Minus 3 into 10 to the power 3. Okay, minus 3 into 10 to the power 3. So this implies lambda 2 is equal to 2 pi epsilon 0 r, we'll take upstairs. So minus 3 into 10 to the power 3 into 2 pi epsilon 0 r, that's it. Yeah, that's it. So minus 3 into 10 to the power 3, this I can write as 4 pi epsilon 0 r, then divided by 2. I'm multiplying by 2 and dividing by 2. And then we have this r. So let's substitute the values. Minus 3 into 10 to the power 3 divided by 2 into 4 pi epsilon 0 r is 1 by 9 into 10 to the power 9 into 10 to the power 9. Remember, 1 by 4 pi epsilon 0 is 9 into 10 to the power 9. 1 divided by 4 pi epsilon 0 is 9 into 10 to the power 9. So we are having inverse here. So we are having inverse here also. 1 by 9 into 10 to the power 9. Then we have r. R is 3.5 meters. So everything is an SI system. What we'll get will also be an SI system. So now this implies lambda 2 is equal. So we have to work out this thing. This is 3 into 3. So 3.5 divided by 6. Then we'll have 10 to the power 3. 10 to the power 9 will go upstairs. So we'll have 10 to the power minus 6. I have already worked this out. This comes out to be 0.58 into 10 to the power minus 8. 0.58 into 10 to the power minus 8. Or I can write 5.8 into 10 to the power minus 9. We have used everything in SI system, so unit will be coulomb per meter, SI system again. 5 and the minus sign also, this minus sign here. So this is minus, this is minus. Minus 5.8 into 10 to the power minus 9, or lambda 2 is equal to minus 5.8 microcoulomb per meter. Okay, microcoulomb per meter. So this cylinder is not positively charged. Okay, this cylinder is not positively charged. This is negatively charged. With a charge density, charge per unit length of minus 5.8 microcoulomb per meter. Okay, that's what we have to find out. That'll do for this session.